Refrigerants are substances that are used to absorb and transport heat for the purpose of cooling. The most common refrigerants used in mechanical refrigeration systems today are refrigerant 123 or 123A, R134A, and R22. Brines are secondary refrigerants and are generally used where temperatures are required to be maintained below the freezing point of water. Brine is a solution of salt in water. The brines commonly used are calcium chloride, sodium chloride or common salt, and glycols such as ethylene glycol, propylene glycol, and so on. In this module, we will learn about the refrigerants and brines. By the end of this module, you will be able to explain the primary and secondary refrigerants, identify the nomenclature of commercial refrigerants, outline the thermodynamic and thermophysical properties, list the environmental and safety properties, list the synthetic, natural, and blended refrigerants, describe brines and properties of brines. Fluids suitable for refrigeration purposes can be classified into primary and secondary refrigerants. Primary refrigerants are those fluids which are used directly as working fluids, provide refrigeration by undergoing a phase change process in the evaporator. Secondary refrigerants are those liquids, air, water, and brines, which are used for transporting thermal energy from one location to other. Antifreezes or brines are used when refrigeration is required at sub-zero temperatures. Unlike primary refrigerants, the secondary refrigerants do not undergo phase change as they transport energy from one location to other. Let us next understand the classification of fluids used as refrigerants. Here we can observe classification of fluids used as refrigerants. Major classifications are pure fluids and mixtures. Pure fluids can be further classified into chlorofluorocarbons refrigerants or CFC, hydrofluorocarbons refrigerants or HCFC, hydrofluorocarbons refrigerants or HFC, and natural refrigerants. Mixtures are subclassified into zeotropic refrigerants and azeotropic refrigerants. Let us next understand the safety classification of refrigerants. Safety classification consists of two alphanumeric characters. Example, A2. The capital letter corresponds to toxicity and the digit to flammability. Refrigerants are divided into two groups according to toxicity. Class A signifies refrigerants for which toxicity has not been identified at concentrations less than or equal to 400 parts per million. Class B signifies refrigerants for which there is evidence of toxicity at concentrations below 400 parts per million. Next, let us learn about classification according to flammability. Refrigerants are divided into three groups according to flammability. Class 1 indicates refrigerants that do not show flame propagation when tested in air at 21 degrees centigrade and 101 kilopascals. Class 2 indicates refrigerants having a lower flammability limit of more than 0.10 kg per meter cube at 21 degrees centigrade and 101 kilopascals and a heat of combustion of less than 19 kilojoules per kg. Please refer standard number 34 in ASHRAE Handbook of 2013 version. Class 3 indicates refrigerants that are highly flammable as defined by a lower flammability limit of less than or equal to 0.10 kg per meter cube at 21 degrees centigrade and 101 kilopascals, or a heat of combustion greater than or equal to 19 kilojoules per kg. Let us next understand the refrigerant classification based on safety. Refrigerants are classified as Grade A, Grade B, Grade C with respective to safety groups. Most of the companies follow and use A-grade refrigerants because these refrigerants have no identification of flammability and are non-toxic in nature. These are the essential properties of refrigerants. We can observe various safety codes designation from the images. Now let's move on to learn more on designations of refrigerants. All the refrigerants are designated by R followed by a unique number. Fully saturated halogenated compounds refrigerants are derivatives of alkenes such as methane and ethane. These refrigerants are designated by R XYZ, where X plus 1 indicates the number of carbon, that is C atoms. Y minus 1 indicates number of hydrogen H atoms. And Z indicates number of fluorine F atoms. The balance indicates the number of chlorine atoms. Only 2 digits indicate that the value of X is 0. Let's next look at some chemical formulas. Given here is the chemical formula for R22. Now, let's learn what is an inorganic refrigerant. Inorganic refrigerants are designated by number 7 followed by the molecular weight of the refrigerant. Example, ammonia. Molecular weight is 17, therefore the designation is R717. Carbon dioxide. Molecular weight is 44, therefore the designation is R744. Water. Molecular weight is 18, therefore the designation is R718. Let's next learn about refrigerant mixtures. Azeotropic blends behave as a single component refrigerants even though they are blends. Azeotropic mixtures are designated by 500 series, whereas zeotropic refrigerants are designated by 400 series. Zeotropic refrigerants are blends of 2 or more components whose equilibrium vapor, phase and liquid phase compositions are different at given pressures. Let's next discuss the serial numbering used for refrigerant classes. Series numbering for refrigerant classes is as follows: 000 methane based, 100 ethane based, 200 propane based, 300 cyclic organic, 400 zeotropes, 500 azeotropes, 600 organic, 700 inorganic, 1,000 unsaturated organic. Now, let's understand the refrigerant selection criteria. Selection of refrigerant for a particular application is based on the following requirements: thermodynamic and thermophysical properties, environmental and safety properties, and economics. Let's learn about each of these. Thermodynamic and thermophysical properties are suction pressure. At a given evaporator temperature, The saturation pressure should be above atmospheric for prevention of air or moisture ingress into the system and ease of leak detection. Higher suction pressure is better as it leads to smaller compressor displacement. Discharge pressure. At a given condenser temperature, the discharge pressure should be as small as possible to allow lightweight construction of compressor, condenser, etc. Pressure ratio should be as small as possible for high volumetric efficiency and low power consumption. Latent heat or vaporization should be as large as possible so that the required mass flow rate per unit cooling capacity will be small. Thermodynamic and thermophysical properties. Isentropic index of compression should be as small as possible so that the temperature rise during compression will be small. Liquid specific heat should be small so that degree of subcooling will be large, leading to smaller amount of flash gas at evaporator inlet. Vapor specific heat should be large so that the degree of superheating will be small. Thermal conductivity. Thermal conductivity is both liquid as well as vapor phase should be high for higher heat transfer coefficients. Viscosity. Viscosity should be small in both liquid and vapor phases for smaller frictional pressure drops. The normal boiling point indicates the useful temperature levels as it is directly related to the operating pressures. A high critical temperature means a smaller compressor superheat and smaller flash gas losses. On the other hand, since the vapor pressure will be low when critical temperature is high, the volumetric capacity will be lower for refrigerants with high critical temperatures. For most of the refrigerants, the ratio of normal boiling point to critical temperature is in the range of 0.6 to 0.7. Thus, the normal boiling point is a good indicator of the critical temperature of the refrigerant. Let's next learn about environmental and safety properties. Ozone depletion potential (ODP). Since ODP depends mainly on the presence of chlorine or bromine in the molecules, refrigerants having either chlorine, that is, CFCs and HCFCs, or bromine cannot be used under the new regulations. This is why R11 and R12 are phased out and R22 is being phased out. Global warming potential (GWP). Refrigerants should have as low a GWP value as possible to minimize the problem of global warming. Refrigerants with zero ODP but a high value of GWP, example R134A, are likely to be regulated in future. Total Equivalent Warming Index (TEWI). The factor TEWI considers both direct, due to release into atmosphere, and indirect, through energy consumption, contributions of refrigerations to global warming. Toxicity. Some fluids are toxic even in small concentrations. Some fluids are mildly toxic, that is, they are dangerous only when the concentration is large and duration of exposure is long. Flammability. The refrigerants should preferably be non-flammable and non-explosive. Refrigerants R11, R12, R22, R134A, R744, R718, are least hazardous. Given here are the important properties of a refrigerant. Chemical stability inside the refrigeration system. Compatibility with common materials of construction. Miscibility with lubricating oils. Oil separators have to be used if the refrigerant is not miscible with lubricating oil, example ammonia, to ensure oil return to the compressor. Dielectric strength. This is an important property for systems using hermetic compressors. For these systems, the refrigerants should have as high a dielectric strength as possible. Ease of leak detection. In the event of leakage of refrigerant from the system, it should be easy to detect the leaks. Let's now understand the economic properties. The refrigerant used should preferably be inexpensive and easily available. However, cost, which is usually a consideration in all sections, should not influence the choice of a refrigerant since it generally has little economic bearing on the normal refrigeration system. Let's now learn about synthetic refrigerants. Synthetic refrigerants that were commonly used for refrigeration, cold storage, and air conditioning applications are R11, CFC11, R12, CFC12, R22, HCFC22, R502, CFC12 plus HCFC22, and so on. However, these refrigerants have to be phased out due to their ozone depletion potential, that is the ODP. The synthetic replacements for the older refrigerants are R134A, HFC134A, and blends of HFCs. Generally, synthetic refrigerants are non-toxic and non-flammable. However, compared to the natural refrigerants, the synthetic refrigerants offer lower performance and they also have higher global warming potential, that is GWP. As a result, the synthetic refrigerants face an uncertain future. Let's now learn about natural refrigerants. The most commonly used natural refrigerant is ammonia. This is also one of the oldest known refrigerants. Ammonia has good thermodynamic, thermophysical, and environmental properties. However, it is toxic and is not compatible with some of the common materials of construction such as copper, which somewhat restricts its application. Other natural refrigerants that are being suggested are hydrocarbons and carbon dioxide. Though these refrigerants have some specific problems owing to their eco-friendliness, they are being studied widely and are likely to play a prominent role in future. These refrigerants are synthetic refrigerants and are non-toxic and non-flammable. R11 was primarily used with centrifugal compressors in air conditioning applications. R12 was used primarily in small capacity refrigeration and cold storage applications. R22 and R502 were used in large systems such as large air conditioning plants or cold storages. In view of the environmental problems caused by the synthetic refrigerants, natural refrigerants and their blends are gaining popularity. Let's next look at the heat transfer comparisons. The value of the evaporating and condensing film coefficient is an important factor, but other factors to be considered for efficient heat transfer are tube wall resistance, including extended surface if any, air or water film coefficient, refrigerant pressure drop per circuit which affects the mean effective temperature difference, surface ratio of tube outside surface to inside surface. Fouling factors, water-cooled condensers. A cooling coil normally has considerable extended surface on the air side of the tubes. When cooling coil is designed to permit a normal pressure drop with refrigerant 22, higher evaporating film coefficient, it may have a rather large pressure drop with refrigerant 12 or 500, resulting in lower mean effective temperature difference. Water-cooled condensers using refrigerant 22 normally provide a greater capacity than those using refrigerant 12 or 500. Air-cooled condensers have considerable extended surface on the air side of the tubes. The higher evaporating film coefficient or refrigerant 22 combined with the extended surface results in a significant increase in the overall heat transfer rate. Normally, evaporative condensers use prime surface tubing without extended surface on the outside of the tubes. Where the unit is designed for refrigerant 12 or 500, there is no significant increase in capacity when using refrigerant 22. Let's next learn about brines. At temperatures about 32 F, water is the most commonly used heat transfer medium, secondary refrigerant. At temperatures below 32 F, freezing point of water brines are used. Brine is a solution of salt in water. When salt is mixed in water, then the freezing temperature of the solution becomes lower than that of the water. This is due to the fact that salt, while dissolving in water, takes off its latent heat from the solution and cools it below the freezing point of water. Three types of brines used are an aqueous solution of inorganic salts, that is, sodium chloride or calcium chloride. For low temperatures, an eutectic mixture may be used. An aqueous solution of organic compounds, that is, alcohols or glycols, ethanol water, methanol water, ethylene glycol, and propylene glycol are examples. Chlorinated or fluorinated hydrocarbons and halocarbons, these are expensive. Let's understand the factors to be considered when selecting a brine. When selecting a brine, the following factors need to be considered. Freezing point. Brine must be suitable for the lowest operating temperature. Application. When using an open piping system, the possibility of product contamination by the brine should be checked. Cost. The initial charge and quantity of makeup required are factors in the determination of cost. Safety, toxicity, and flammability of brine. Thermal performance. Viscosity, specific gravity, specific heat, and thermal conductivity are utilized to determine thermal performance. Suitability. Piping and system equipment material required a stable and relatively corrosive-free brine. Codes. Brine must be acceptable by codes, ordinances, regulatory agencies, and insurer. Let's study the opinion of using calcium chloride or sodium chloride as brine. The most common brines are aqueous solutions of calcium chloride or sodium chloride. Although both of these brines have the advantage of low cost, they have the disadvantage of being corrosive. To overcome corrosion, an inhibitor may be added to the brine. Sodium dichromate is a satisfactory and economical inhibitor. Sodium hydroxide is added to keep the brine slightly alkaline. Sodium chloride is cheaper than calcium chloride. However, it cannot be used below its eutectic point of -6 Fahrenheit. It is preferred where contact with calcium chloride brine cannot be tolerated. For example, with unsealed foodstuff. The use of calcium chloride of commercial grade is not satisfactory below -40 Fahrenheit. Let's study the option of using alcohol solutions. Systems using aqueous solutions of alcohol or glycol are more susceptible to leakage than those using salts. A disadvantage of alcohol is its flammability. It is utilized mainly in industrial processes where similar hazards already exist and in the same temperature range as the salts, down to -40 Fahrenheit. The toxicity of methanol water, wood alcohol, is a disadvantage. Conversely, the non-toxicity of ethanol water, denatured grain alcohol, is an advantage. Corrosion inhibitors should be used with alcohol-type brines as recommended by the manufacturer of the alcohol. Let's understand glycols. Aqueous solutions of glycol are utilized mainly in commercial applications as opposed to industrial processes. Ethylene and propylene glycol possess equal corrosiveness, which an inhibitor can neutralize. Galvanized surfaces are particularly prone to attack by the glycols and should be avoided. An inhibitor and potable water are recommended for making up glycol brines. Glycols can be used as heat transfer media at relatively high temperatures. Let's understand the piping system to be used. All materials in the piping system include flange gaskets, valve seats, and packing. Pump seals and other specialities must be compatible with the brine. Copper tubing, except for the salt brines, and standard steel pipe are suitable for general use. The pump rating and motor horsepower should be based on the particular brine used and the actual operating temperature. Next, let's look at the properties of brine. High values of specific gravity, conductivity and specific heat, and low values of viscosity promote a high rate of heat transfer. High values of specific gravity and viscosity result in high pumping head and consequently high pumping costs. High specific heats are desirable in that they reduce the quantity of liquid required to be circulated or stored for a given duty. Low viscosities are desirable from a standpoint of both rate of heat transfer and low pumping cost. They are particularly desirable at the lower temperatures where the viscosity increases. Let's understand the color codes of cylinders. Given here are refrigerants with specific cylinder colors as per ASHRAE Standard 34. CFC's refrigerants. R11 orange color cylinder, R12 white color cylinder, R13 light blue, R502 light purple color cylinder. HCFC's refrigerants. R402B green brown olive, R408A medium purple, R409A medium brown tan. HFC's refrigerants. R23 light blue grey, R134A light sky blue color cylinder, R410A rose color cylinder, R507 blue green teal, R508B dark blue navy, R22 light green color cylinder, R123A light blue grey. Other refrigerants are 717 silver or black color cylinder. R744 thick green color cylinder. Here, refrigerants with specific cylinder colors has been shown as per ASHRAE. CFC's refrigerants: R11 orange color cylinder, R12 white color cylinder, R13 light blue, R502 light purple color cylinder. HCFC's refrigerants: R402B green brown olive, R408A medium purple, R409A medium brown or tan. HFCs: R23 light blue grey, R134A light sky blue color cylinder, R410A rose color cylinder, R507 blue green teal, R508B dark blue navy, R22 light green color cylinder, R123A light blue grey. Other refrigerants: R717 silver or black color cylinder, R744 thick green color cylinder. Given here is more color coding for different cylinders. Before we conclude, let's take up an activity. Let us quickly recap the key points of this module. In this module, we have learnt that fluids suitable for refrigeration purposes can be classified into primary and secondary refrigerants. Major classifications of refrigerants are pure fluids and mixtures. Safety classification consists of two alphanumeric characters. Refrigerants are divided into two groups according to toxicity. Refrigerants are divided into three groups according to flammability. Refrigerants are classified as Grade A, Grade B, Grade C with respective to safety groups. All the refrigerants are designated by R followed by a unique number. Inorganic refrigerants are designated by number 7 followed by the molecular weight of the refrigerant. Selection of refrigerant for a particular application is based on the thermodynamic and thermophysical properties, environmental and safety properties, and economics. Synthetic refrigerants that were commonly used for refrigeration, cold storage, and air conditioning applications are R11, CFC11, R12, CFC12, R22, HCFC22, R502, CFC12 plus HCFC22, and so on. The most commonly used natural refrigerant is ammonia. Brine is a solution of salt in water. The most common brines are aqueous solution of calcium chloride or sodium chloride. Refrigerants follow specific cylinder color as per ASHRAE standard.